Yes, sir. Yes, sir. Here you can.
So there are some questions.
Yes, sir. These are the questions that they posted through the Google response sheet, sir.
AC भी नहीं चल रहा है.
See, it's
AC is not running.
Temperature is high and reduce it, sir.
What is that?
Temperature, no, sir.
How to solve the magnetic theory of Coulomb? Not related sums. AQ आपसे स्पेशल इसका बुक पढ़ाते टाइम स्टूडेंट का क्या क्या ध्यान रखना चाहिए कि क्या क्या करना चाहिए इस टाइम. सर बुक पढ़ने के साथ उसका नोट भी बनाना चाहिए. बुक नहीं हम डिजाइन कर रहे हैं.
Sir, you have any tissue paper to wipe tissue paper You can skip, sir, if you're unable to follow anything.
Why does
Sir,
only time as the fourth answer? Why can't I some other physical quantity? It does.
thank you. Yes. So would you like to have some water, sir?
Nah, water is
Also, if you want to write something, sir, then call me, sir, so that I will swap the camera, so that the writing part will be visible, sir.
okay.
I'll be here, sir. I'll be
Oh,
here.
yeah, you
I'll be
did.
assisting you, sir.
But there's no cameraman on it?
No, sir, this is the one.
Okay.
Webcam with a mic, sir.
Okay.
So, or fine.
Pani pila do.
Either.
You want to start now? Or
Yes, sir.
what?
We will start, sir. Already. Let me just stand, sir. Let me just check the camera position. Yeah, I think it's fine, sir.
Yeah.
That will be delay 15-20 seconds, sir. Here.
Yeah, that's fine.
So you can go ahead, sir.
Yeah.
Sir, can you just?
How do we go? Say something, okay? Good evening.
Yeah, already I
Okay.
introduced.
Hello?
Yeah.
Hello?
Yes, sir. We are audible only, sir.
No, but how come the photo
Otherwise-
is coming now?
I told no, sir. Like 15-20 seconds delay will be.
No,
there.
it's much more.
And then speaker I turned it off. Otherwise echo will go, sir.
Okay.
Yeah. But
Hello?
we are live, sir. We are live only, sir.
There's nobody. Hello?
No, sir. We are live. We won't get the audio part, sir.
I see.
Yeah.
So what am I supposed to do now?
No, you can start speaking, sir. Questions will come here.
Okay. Hello, I'm ready now. So if you have any questions, good evening.
Audible, sir. Yeah.
Yeah, please. Who all are there? Can I start writing?
You want to, if you want to write something, you have to come here, sir, and then start writing. And at the time, you have to swap this camera to this mode, sir.
Okay.
Whatever is visible here will be shown to the students, sir.
Where do I write?
Here, sir. Yeah, here, sir.
Okay. But I'm not getting no response.
No, their audio won't come, sir. Only they will type the questions.
So where is the question?
Here, sir. It is already here, no, sir.
Where is the question?
Here, sir.
Okay.
Sir, this headphone shall be removed, sir. Otherwise, it will be confusing, sir. Echo will come, sir.
So let me start with Ohm's law and Lorentz force law cannot be explained by. So these two laws do not come under electromagnetism. Okay. So let me write the answer here. Oh, Ohm's law.
It's not writing, sir. Let me just find out, sir.
Where is everybody?
I'll just.
There's no status.
You can start, sir. You can skip that question. We are
What
trying
do I
to
do?
find.
What do I do then?
This question will come again.
No, but how do I write?
That's what, sir. We need to wait, sir, till our technical people come.
They must be waiting, those people. So
Yes.
what do we tell them?
Right, sir.
So there's a technical difficulty or something. What's the bolo hai?
1 second. Sir. We'll simply tell them.
I can write the questions here. Answers here.
Yeah, you can write
Yeah.
also.
So I'll write the answer here.
Right, sir. Then shall I remove it, sir?
Yeah. Now that is better.
Yes.
Okay. So this. Question.
Sir, stainless is not right.
Describe.
Is it right, sir?
लिखेगा अभी?
नहीं लिखने वो उसका देख रहा था
नहीं लिख रहा.
नहीं लिख रहा
लिख ही नहीं रहा. टूटा रहा था.
So this can we post, sir, or you want to complete it, sir?
Oh no. So इसको post कर दो.
Yes, sir.
Then I will write it.
Yes, sir. Yeah. I think we exceeded the maximum limit, that's why, sir. So we'll split it into 2, sir.
Electro.
So this part we'll cut and paste it below, sir.
Cut.
Yes. I think it will work, sir. This post it, sir, and then again post the other one, sir. Post. Yeah, sir. Can you just check, sir? This.
That answer has gone, huh?
Yes, sir. It's gone, sir. Other stainless won't work, sir, here.
देख लेता है
I'll answer in the meantime and then.
Right, sir. Other questions.
How do we go there?
Yeah, I have to keep this thing. And then here, sir. Yeah.
Okay.
also you can answer, sir.
Hmm?
इसको ना रीस्टार्ट करना
Oh, but right
No, you
now
can't
we
do
can't
that.
do
पड़ेगा।
that.
हो सकता है।
Yes, sir.
चलो यहीं पर लिखते हैं.
So orally you can explain, sir, and then writing part alone we will skip,
Okay.
sir. Yes, sir.
So, Manish, I've just written to you that the Lorentz force is a force experienced by a charged particle when fields are applied. Maxwell's equations give you the dynamics of the field. All right. So, for example, the Gauss's law, that divergence of B is 0 and divergence of the electric field is related to the charge, give you the geometric effect, how the field lines change, and dynamically by changing fields, how they change come from Faraday's law and the displacement current and the curl of the equations. So that's the answer. The Ohm's law is an empirically seen law, right? You must have read that semiconductors do not follow Ohm's law. So it's an empirical law that metals are seen to follow, and it is the effect of the field. Similarly, the other one, Lorentz force, is the force law, what fields do to the charge. Manish, you're right. Is saying that right on the board explaining in details. This is not a board behind me. It's actually a screen. Manish, your question, are there 4 Maxwell's equations or 5 Maxwell's equations? Number of Maxwell's equations are 4. And as I said earlier, they describe how the fields behave in presence of charge. So this is to do actually with how the fields are generated and what their behavior is. Okay, Jainarayan Dubey has asked, if there's a monopole exists in nature, how does the Maxwell's equation will transform? If there's magnetic monopole, then you would have the divergence of B will not be 0, and in the dynamics part there will be a magnetic current that will also give rise to the curl of E. So there will be a perfect symmetry between Faraday's law and the Faraday's law, which relates curl of E to the changing magnetic field, and in addition there will be a magnetic current also. Another question. So let me take other questions from here. Okay, now there's a question by Nupur. This was sent over the mail, and the question says, why does superposition principle not hold for potential energy of charges? But who said so? Just like electric field at a point can be written as the sum of the electric fields of individual charges. That is what the principle of superposition is. Similarly, potential at a point can also be written as the superposition of charges due to superposition of potential due to different charges. Remember, superposition depends on the linear dependence. As long as quantity A depends on quantity B in a linear manner, that is, A is proportional to B. In our case, electric field is proportional to the charge, or the potential is proportional to the charge, then it's a linear behavior and the principle of superposition will hold. Recall, I use this. If you've gone through the lectures carefully, when I use derived the reciprocity theorem for you, where we related the potentials
due to one charge multiplied by charge from the other side to the potentials due to the previous charge and the other charges. I used superposition principle for the potential because I said that potential varies linearly with charge. So, the question that why does superposition principle not hold for potential energy of charges is not correct. It does. Okay, then there's a question by Meher Pedwekar, and it has to do with active magnetic bearings, and it says there's a magnetorestriction effect. It may lead to expansion or contraction of stator or rotor. Yes, it does. I mean, any restriction effect, I mean, whenever things are going back and forth, it will have some sort of effect in fatigue of the material. However, it will be very negligible. Unless things are going really moving very, by large amount, it will not be that much. Okay. Now, next question is by J. Narayan Dubey. If we draw a line and suppose there is a charge minus 2q at the center and plus q charges at the endpoints, how can I calculate its charge density? If you look at the charge density at the points, this will be a superposition of delta functions. So, minus 2q at the center, which I'll take to be the origin, then that will give a charge density of minus 2q delta r. And at the endpoints, suppose the line length is 2l and a charge plus q is at the minus l and plus q is at plus l, then the total charge density will be delta x minus l times q plus delta x plus l times q minus 2q delta x. This is the linear charge because I'm writing x. If it is a three-dimensional density, then you just replace it by r vector. Okay, now this is a question by Gaurav Vyas. Gaurav Vyas says, what holds negatively charged electrons together? Well, what are we talking about? Are we talking about metals? If we are talking about metals, in metals there is a balancing positive charge. If we are talking about atoms, there is a nuclei which hold the electrons together. So it's the balancing positive charges that bring them together and somehow overcome the repulsion. Right? They are distributed, so repulsion may not be as high. So you have to work out the details. But there is always a balancing charge. If I just put two electrons or many electrons at one place without any other charges, they will not be held together. Now, this is another question by Gaurav Vyas, who says that question is not related to the course, but how theory of relativity can be understood on graphene electrons without accelerating them to the speed of light. Okay, so it is not the theory of relativity. What it is that in graphene, the dependence of energy on momentum of electrons comes out to be linear. That is, the energy is proportional to the momentum magnitude. This is the case for photons. For example, photons have energy E equals pc, the momentum times c. So this linear behavior is a very relativistic effect, and that's how you can kind of relate the energy to the momentum in a linear manner, and that is what you call the relativistic effect. It's not that the particles are moving at speed of light. It's the behavior of or the dependence of the energy on the momentum in a linear manner. Now, question 3 by Gaurav Vyas. Is it true that nuclear power plant, it is not really nuclear energy that we are using? We are using electrical energy? No, this is not true. We are using nuclear energy to generate heat, which in turn heats water, and that water runs a turbine that creates electricity. Okay, now let me come back to the questions which are written here. Okay, I'm unable to listen anything. This is in general we say magnetic monopole. I have answered. Okay, now Princey Agrahari says in Griffiths it is written that current is actually a vector. Then why we usually take it as a scalar? Okay. Now the question is, what convention do I follow? All right. I can say that current is a vector, then the length of the wire or length segment I'll treat as a scalar. Recall when in my lectures I sometimes switch between the current and the L vector, right? So it is how I want to do things. It is convenient to take L as a vector because then I can relate it to the length of the or length segment of a wire as a vector, because then I can relate it to its area, its volume. So it's better to take I, the current out, as a scalar and then use the vector sign over the length of the wire. Then that becomes a geometric thing. All right. So current does flow in one direction. So it's up to me. Where do I want to put the vector sign? Which one do I want to treat as a vector? Now this is also related to the other question. That is, current is a scalar or a vector. This is by Jenner and Dubey, and I hope I have answered your question. It has a direction, and that direction does have effect, for example, in creating a magnetic field. But it's up to me where I want to put the sign, whether I put it over the length segment or the current density. Okay. Then the next question is Himanshu Morjaria. He says, please explain how Ohm law generate in the complete circuit. I don't understand the question. Could you please rewrite it in a better way? Because how Ohm's law generate in the complete circuit? You mean to say complete circuit में Ohm's law कैसे पैदा हो जाता है? ये मेरे को समझ में नहीं आया क्वेश्चन, तो जरा आप बता दीजिए तो अच्छा रहेगा. मैं इंतजार कर रहा हूं और क्वेश्चंस का. आई एम वेटिंग फॉर मोर क्वेश्चंस. आप लोगों से एक रिक्वेस्ट और है, जब कभी आप क्वेश्चन पूछते हैं फोरम पे, मैं सुबह शाम दोनों टाइम देखता हूं, जब आपको आंसर मिल जाए एक टिक कर दीजिए कि आंसर मिल गया, ठीक हो गया, आपको समझ में आ गया. तो उससे मेरे को थोड़ा ठीक रहता है. नहीं तो मेरे को लगता है पता नहीं आपने देखा नहीं देखा, समझ में आया नहीं आया आपको. इफ यू जस्ट से आंसर्ड और कंप्लीटली आंसर्ड और अंडरस्टूड, दैट विल रियली हेल्प. ओके, Janaran Dubey sir, please explain about final exams. What do you want me to explain? It's going to be 50 questions, 20 from assignments, 20 from lectures, and 10 new questions. So 20 will be based on lectures. That means, whatever I've solved in lectures or some concept that I have given, I'll ask question about that. 20 questions will be based on assignments, and so work on your assignments properly. And 10 will be new questions that will be really testing you, what you understand. अच्छा, Cosmos says, please add simple questions for the assignment. Those in the assignments are a bit hard for me. ठीक है, लेकिन अब आपको थोड़ा मैं चैलेंज भी करता हूँ, इसीलिए आप जब लोग क्वेश्चन पूछते हैं, when you ask questions, I don't directly answer them, right? I say, please work this out, and it has worked out very nicely because some of you have gone back and worked out the questions, and that must have helped you understand things better. तो थोड़ा तो चैलेंज करेंगे, लेकिन ठीक है, ऐसा चिंता मत करिए. चंदन झा पूछ रहे हैं, what is the condition to put delta function in potential electric field? Delta function is not put in electric field or potential. Actually, we put delta function to describe a density of a point particle. And as I explained in my lectures, the mass density is m times delta for a point particle. Charge density for a charged point particle is q times delta. Delta at that particular point. Okay, Manish has asked a question, is there a physical significance of magnetic vector potential? I answered this in detail in one of the questions which was raised in the forum, and the answer is directly no, but in advanced courses we do work out that this is related to momentum of the particle. And the question, when I answered this on the forum, I said, work out q times the vector potential and you will see its dimensions. And those dimensions will give you an idea that this can be related to the momentum of a particle. So this is more for advanced courses, but loosely, yes, it can be related to momenta of the particle or the fields. Okay. Princey Agrahari asks, I am preparing for TIFR. What tips would you give to give the strategy? Princey, unfortunately, in studying and the way I do my physics, I don't follow any strategy. It is like just sit, work hard. If we try to do strategy and all that, then we are becoming more like, the traders. Baniya. And I don't want to be that. I'm an academic. I take challenging problems, solve them. And that's how you should be, and that's what make you grow as an academician or as a student. I'm waiting for questions. चंदन जा फिर से पूछ रहे हैं, बताइए बुक को इफेक्टिव तरीका क्या है पढ़ने का और नोट बनाना। ये देखिए बहुत बहुत इंडिविजुअल डिपेंड करता है और अलग अलग मौके पे डिपेंड करता है, किस टाइप की किताबें पढ़ रहे हैं उस पर डिपेंड करता है। मैं कई बार अंडरलाइन करके भी पढ़ता हूँ, कई बार मैं बहुत तेजी से भी पढ़ता हूँ, कई बार बहुत धीरे से भी पढ़ता हूँ, कई बार नोट्स भी बनाता हूँ। तो ये अलग अलग क्या आपके रिक्वायरमेंट्स हैं, क्या आप समझना चाह रहे हैं। सपोज आप एक न्यूज़पेपर पढ़ रहे हैं, उसमें शायद आप नोट्स ना बनाएं, लेकिन जब आप एक किताब पढ़ रहे हैं उसमें आप नोट्स बनाएंगे, साइड में क्वेश्चंस भी लिखेंगे। और मेरे को एक बड़ी अच्छी बात आपकी लगी कि आप किताब पढ़ रहे हैं, तो किताब पढ़ने में साइड में क्वेश्चंस लिखिए, कोई आंसर दिया वो लिखिए। बेसिकली वो सब करिए जिससे आप इसको दोबारा से जब देखना चाहें तो देख सकें, चाहे वो नोट्स बनाना हो या दिमाग में अगर रख सके तो दिमाग में रखिए। लेकिन ये कई तरीके हैं और हर तरीके को आपने ट्राई करना चाहिए, क्योंकि एक तरीका हर तरफ नहीं लगता है। इनफैक्ट मैं तो जब अखबार पढ़ता हूँ, मैं जो शब्द मेरे को समझ में नहीं आते हैं मैं उनको भी अंडरलाइन करता हूँ, जिससे बाद में उनको देख सकूं। तो आइडिया ये है कि जो कुछ आप पढ़ रहे हैं उसको रिटेन कर रहे हैं नहीं कर रहे हैं, कैन यू रिटेन इट, या आपके पास रहता है नहीं रहता। उसके लिए जब तक आप कोई भी जो भी करना चाहें, नोट्स बनाना चाहें, साइड में लिखना चाहें, दिमाग में रखना चाहें, अपने कमरे की दीवार पे लिखना चाहें, वो आप पे डिपेंड करता है। तो कोई एक तरीका नहीं है इसका। मनीष बोलता है क्वेश्चंस आर हार्ड, सम इंटीग्रल्स डिवाइडेड इनटू 3 पार्ट्स एंड दिस अगेन वाज एन मल्टीपल इंटीग्रल। मनीष और आप सब लोगों से ये कहना चाहूंगा, देखिए ये इंटीग्रल अच्छी मैथमेटिक्स करना लाइफ का पार्ट है। जब भी आप कुछ अच्छी इंजीनियरिंग करेंगे या साइंस करेंगे, अब तो बायोलॉजी में भी काफ़ी मैथ्स होती है, तो मैथ से डरिए मत, और डरने की ज़रूरत भी नहीं है। थोड़ा टाइम लगता है, बस थोड़ा पेशेंस रखिए, थोड़ा पढ़ना लिखना, ये मैथ्स करना टेस्ट क्रिकेट टाइप की चीज़ है, T20 नहीं है, तो टेस्ट क्रिकेट खेलिए आप थोड़ा। अच्छा, अब जय नारायण दुबे बोलते हैं, सर वेयर डिड यू टेक द असाइनमेंट क्वेश्चंस फ्रॉम। जय नारायण, ये क्वेश्चन ज़्यादातर तो मैंने खुद बनाए हैं, तो आप अगर गूगल में ढूंढेंगे या आपकी किताब में ढूंढेंगे तो आपको नहीं मिलेंगे, क्योंकि एक पढ़ाने का आप लोगों को खास तौर पे जब हम मूक कोर्स कर रहे हैं तो मैं टीएस को भी बोलता हूँ, मैं खुद को भी समझाता हूँ कि हम लोगों को बहुत पूरे कंट्री में सब लोगों को पढ़ाना है, तो क्वेश्चंस नए होने चाहिए, ऐसे नहीं होने चाहिए कि अपना देख के कहीं से जवाब दे सकें, तभी वो इफेक्टिवली सीखेंगे। थोड़ा तो क्वेश्चन थोड़ा टफ भी बनाते हैं, थोड़े इजी भी बनाते हैं, तो क्वेश्चन ज़्यादातर हम खुद बनाते हैं। अच्छा, प्रिंसी बोल रही है, यस मैग्नेटिक वेक्टर पोटेंशियल वाज शोन टू हैव डायमेंशंस ऑफ मोमेंटम। मैग्नेटिक वेक्टर पोटेंशियल टाइम्स द चार्ज, राइट। सो जय नारायण बोल रहे हैं, इट्स वेरी गुड, थैंक यू। आई डोंट नो व्हाटएवर यू आर सेइंग इज गुड, आई टेक इट एज अ कॉम्प्लीमेंट, थैंक यू वेरी मच। गौरव बोलते हैं, वी ऑल स्टूडेंट वांट टू स्टे कनेक्टेड विद यू एंड अदर, व्हाई डोंट यू मेक अ प्लेटफॉर्म फॉर दैट अंडर IIT डोमेन। गौरव, थैंक यू वेरी मच कि आप इतना सम्मान दे रहे हैं, लेकिन फोरम से तो हम कनेक्टेड ही हैं। फोरम पे लिखिए, आप जितना लिखेंगे मैं जवाब दूंगा। मैं सुबह शाम दोनों टाइम फोरम पे जाता हूं और आपको जवाब देता हूं। और कोई तरीका है तो आप ईमेल डाल सकते हैं, कुछ कर सकते हैं, मैं जवाब जरूर देता हूं। स्टूडेंट्स के लिए मैं कुछ भी करूंगा। गौरव व्यास, साई लैब बाय IIT रोपर इज वन सच एग्जाम्पल। अब इतना मेरे को पता नहीं है। ओके, कॉस्मोस, सर व्हाई वी यूज वेक्टर डेरिवेटिव, इज इट बिकॉज फंक्शन इज अ वेक्टर। वेक्टर डेरिवेटिव इसलिए यूज करते हैं क्योंकि आप ऐसे सोचिए ना, जैसे जब ग्रेडियंट और डाइवर्जेंस वगैरह समझाया था आपको, उस टाइम हमने दिखाया था कि कोई भी चीज 3 डायरेक्शन में चेंज कर सकती है। अगर जैसे आप पहाड़ की हाइट लीजिए, आप एक डायरेक्शन में जाएंगे एक तरीके से चेंज करेगी, दूसरी डायरेक्शन में जाएंगे दूसरे तरीके से, तीसरी डायरेक्शन में जाएंगे तीसरे तरीके से। अब जब कोई चीज 3 तरफ अलग अलग तरीके से चेंज कर रही है तो उसको बताने का बेस्ट तरीका क्या है कि एक डायरेक्शन दीजिए, एक उसका चेंज का मैग्नीट्यूड दीजिए। जब भी आप डायरेक्शन और मैग्नीट्यूड देंगे वो वेक्टर क्वांटिटी हो जाएगी, इसीलिए वेक्टर डेरिवेटिव्स यूज होते हैं। हाँ, चंदन झा पूछ रहे थे कि मैथमेटिकल टर्म्स थोड़े कठिन हो जाते हैं और फिजिक्स की किताब कैसे पढ़ी जाए। जहां मैथमेटिकल टर्म्स कठिन हो जाए फिर बैठिए और वर्कआउट करिए, है तो वर्कआउट करने से आपके दिमाग में भी रिटेन रहेगा, अगली बार जब अटकेंगे फिर से दोबारा जाके देख सकते हैं। तो इसलिए वही तरीका है, फिजिक्स पढ़िए, मैथमेटिक्स वर्कआउट करिए। You cannot learn mathematics without working it out. So for that, not just making notes, working out in details, and you write each and every step. I hope I have answered you, Chandan. Jai Narayan Dubey, sir, I want to practice some more questions. That is why I am asking. जयनारायण, आप अगर और क्वेश्चन करना चाहते हैं तो आप ग्रिफिथ्स के पहले बहुत सारे क्वेश्चंस हैं, ग्रिफिथ्स में बहुत अच्छे क्वेश्चंस हैं, इसीलिए ग्रिफिथ्स भी आपके लिए फॉलो करी जा रही है। और दूसरी किताब में कोई जानना चाहेंगे तो आप मेरे को फोरम में पूछिए, मैं आपको किताबों के नाम दूंगा। एक है मिलफर्ड एंड क्रिस्टी, वो थोड़ी सी एडवांस है इसलिए उसके बारे में नहीं बोल रहा हूँ। तो ग्रिफिथ्स इज गुड इनफ, बाकी किताब आप लिखिए तो मैं देख के बताता हूँ, आपके लेवल पे कोई मिलेगी तो मैं बताऊंगा जरूर। Cosmos says, sir, can you explain English? I'm weak in Hindi. Okay, Cosmos, you said why we use vector derivatives, so I'll answer that first because I answered this in Hindi earlier. Cosmos, we use vector derivatives because you see when I'm in one dimension, I either go to the right or go to the left. Function changes in only one way. We do df by dx. However, if I'm in 2 or 3 dimensions, I can walk into x direction, y direction, z direction. And when I do that, I change things in 3 directions differently. For example, if I take a hill and if I am on that hill, if I go move in one particular direction, its height may change in one way. If I move in another direction, it may change in another way. For example, if I walk, parallel to the ground, height of hill may not change. If I, climb up the hill, it changes very fast. So I have both magnitude and the direction in which it changes. So whenever I have a magnitude and a direction, I have to do vectors. That's the best way to describe it. That's why I use vectors and vector derivatives to describe. So gradient, for example, tells you about the change in a scalar function in 3 different directions. That becomes a vector quantity. It's a vector derivative. Similarly, I've explained divergence and curl in very detail about flow of fluids, how fluids curl into themselves, and whenever that is happening, you will see that I have to use vector derivatives because I'm describing change in the direction and change in the magnitude both. I hope, Chandan, you're okay. चंदन झा, तनकू बहुत अच्छे से समझाए सर, नेक्स्ट कोर्स थोड़ा बोलने के इसका स्पीड कम करिए सर। तनकू मतलब क्या? चलिए स्पीड तो कम कर देंगे, अभी मेरे को लग रहा था बहुत तेजी से क्वेश्चन आ रहे हैं इसलिए थोड़ा तेज बोल रहा था। I'll slow down now. आप बहुत अच्छे से समझाए हैं सर, थैंक यू सर, प्लीज थैंक यू वेरी मच। आपको अच्छा लगा, अच्छी बात है, स्पीड में स्लो कर दूंगा। वैसे आपको लग रहा है थोड़ा इसको टेप कर लीजिए, बाद में स्लो मोशन में सुन लीजिएगा। अभी मेरे को थोड़ा तेज बोलना पड़ रहा था क्योंकि बहुत तेजी से क्वेश्चंस आ रहे थे, मैं अब स्लो हो जाऊंगा अभी। अगर और कोई क्वेश्चन, देयर आर मोर क्वेश्चंस। So Chandan Jha has said that I have spoken a little fast. That was because the questions were coming very fast. But I'll slow down now that he has given a feedback. Okay, Manish says, okay sir, please do not give assignment type hard questions in the exam. It will take 1 hour to solve one question. Okay Manish, idea is that we do give hard questions in assignments because you have a lot of time to solve them. Exams certainly are not as hard as assignments. Assignments prepare you for the war, and war is not going to be as difficult as the practice. Okay, Gaurav Vyas, can we expect new and more advanced course electromagnetism after completing? If there's a request, I'm willing to give it. There's no problem. I mean, advanced course, the level of Jackson can be given very easily. Okay, Jay Narayan Dubey asks, change in electric field gives rise to not electric field, Jay, it's magnetic field. And what about change in magnetic field? Change in electric field gives rise to a magnetic field. And change in magnetic field gives rise to an electric field. This is a law of nature. Now, how it arises is when you change the electric field, it is equivalent to a current called the displacement current. This is what we have learned by conservation of charge. And that displacement current, whenever there is a current, Biot-Savart law or whatever you want to call it, gives you a magnetic field. Similarly, this is a fundamental law of nature that change in a electric field will always give you magnetic field. I mean, through the displacement current is equivalent to a current. Current gives you magnetic field is a fundamental law, and change in magnetic field gives you electric field. That is also a fundamental law known as Faraday's law. This is how nature works. These are the laws. So we observe and make these laws. Himanshu Morjay, sir, I am a biology student, but I am interested in physics all time. This time I not feel better because I have first time to go through. Well, this happens, Himanshu. Himanshu, next time you will do better. Janaran, yes sir, it was a typing mistake, but Jai, I hope I have answered your question and you hopefully understand. Cosmos, why the unit vectors in polar coordinate depend on position? Okay, Cosmos, you are asking why the unit vectors in polar coordinates depend on position. Well, this is how we define them, right? They are directed in such a way, the way we construct, it's up to us how we construct them. This is how we have constructed them, that they will, R vector will be from the origin to the position of the particle, and therefore if the position changes, the R unit vector will change. And I have also decided that the phi unit vector is going to be perpendicular to R. So if R changes, the perpendicular direction also changes. This is how we have defined them. And once we realize how they change with the position, we work them out properly according to that change. Okay, Manish Bhardwaj says, thank you sir, बात करके बहुत अच्छा लगा आपसे सर, आप इलेक्ट्रोडायनामिक्स को बहुत ही नए और अच्छे तरीके से समझाए हैं. Thank you very much Manish. I hope your learning experience is good and you know you'll gain a lot from this course. Gaurav says, last time I was unable to do your course, solid state physics course, because of lack of quantum mechanics. We want a basic course in quantum mechanics in order to do your SSP course. That course was quite hard to follow. Gaurav, I do have a course in quantum mechanics, and if you want it, send a request to NPTEL and you know we can run it. There's no issue. Janaran Dubey. Sir, why do we take time as our fourth coordinate? Okay, why do we take time as our fourth coordinate? Well, we don't take it, we don't decide it. Nature decides it. When Einstein gave his theory of relativity, he found just like in moving frames, x, y and z become relative. For example, if I'm moving in x direction, in my frame, x will be x in the stationary frame minus vt. But he also found that the time also changes because the speed of light is the same. So time also mixes with the coordinates. That's why time is taken. I mean, the nature gives it. Nature decides it. Right? We don't dictate to nature. What do? We only describe nature. Nature is such that time also is relative. It depends on where we are, how fast we are moving. Janaran Dubey. Why we choose time? Okay, that I have said. Oh, time only. So I hope I have answered your question. X, Y, Z. You can say, why do I choose the distance? It's the same thing. It is found through theory of relativity and then tested again and again through experiments that time mixes with position. I'm waiting for questions. Okay, Gaurav says, we are also reading papers of scientists like Einstein, Planck, Bohr, etc. Do you think it should be done at UG level? Absolutely. There are good papers by Planck, Einstein, Bohr, which are readable at UG level. And I do give, when I teach at IIT Kanpur, I do give students a lot of such papers. If you want, on forum, ask me and I can suggest some papers for you to read. These are very good papers and they are very easy to follow and at the same time give you very good grip on fundamentals. Cosmos, can you explain more about Dirac delta function? Cosmos, may I request you that please send a request on this on the forum and then I can write it better and explain it to you. Is that okay? So please send a question on the forum. Janaran Dubey says basic statistical mechanics. So okay, somebody will have to do it. Okay, Chandan Jha says, please thermal physics or thermodynamics book. Okay, send me forum and I'll send you a book and we can make a course in the future. Sure. What about questions about this course, the material in this course? I'm waiting for that. Cosmos, when I'm talking to you, it sounds like I'm talking, you've seen those movies where we talk to in code words, Cosmos, Dirac. And so it's quite a lot of fun, and referring to you as Cosmos. It's like some secret code of ours. And I'm James Bond. Cosmos, James Bond talking to you. We should also have some fun while doing the course, right? So let's do that. Okay, Manish likes this joke. So that is good. Manish, any more questions? Towards the end of the course, I must tell you, I also do radiation from accelerating charges in a very, very physical way. This usually is not taught in electromagnetic course, but it's so easy and it's so nice to visualize why accelerating charges radiate. So please do go through those lectures very carefully. It will enrich you. Okay, Janaran Dubey asks, what is the physical significance of the complex part of the wave function? How do we picturize it? Jay, may I request you to send me a mail separately, because this is on electromagnetic theory and I don't want to bore other students by talking about quantum mechanics right now. The phase of wave function depends on the complex part, and it does play a role in interference because waves can interfere. I'll stop there on this because other students are more interested right now in electromagnetic theory. But I promise you, if you send me a forum or a mail on my email ID, I'll reply to you. I also have a piece of advice for all of you students, and you're from all over the country. One is I want you to be second to none. I mean, you should be competing with the best in the world. I try to give you all that, all right? And therefore, do go through the lectures carefully. I've collected a lot of material. I've worked very hard on these lectures, and just to convey things to you and giving examples so that you really learn the subject well. I've also, if you notice in the lectures, tried to visualize things. I make a lot of figures. You make that a part of your habit. When you learn something, try to picturize it. When you picturize it, when it makes an image in your brain, you can actually see it and start writing mathematical equations by looking at it. So make that a habit. All right? Okay. Now Chandanja says, what is the use of uniqueness solution? Oh, Chandan, very good question. And I also wrote it in the answer to image problem. Uniqueness says that given a boundary condition, the solution of Laplace's or Poisson's equation is unique. So even if I don't solve the equation, but I put some charges in a configuration so that the Poisson's equation in my region of interest remains the same, and boundary conditions are produced by putting these extra charges, and then I write if they are potential or electric field. It's the answer. It cannot be any different. So that is the use of uniqueness theorem. For example, in image charges, when I take a grounded planar surface and put a charge in front, I say the potential in the region where the charge is going to be given by a superposition of the potential of that charge and an image charge. I can do that because of the uniqueness theorem. Because by putting the charge behind the metallic surface or putting an image charge, I satisfy the boundary condition on the metallic surface, and in the region equations remain the same. So I found the solution, and that is the solution without solving the differential equation. That is the use of uniqueness theorem. Okay. Cosmos, sir, what is the solution of Laplace equation simple case when those, what are those simple cases? Okay. Laplace solution, spherical, cylindrical, symmetry cases, these are very simple cases. For example, I know if there is a charge in a spherical charge distribution, then the outside, the potential is charge divided by r, 1 over 4 pi epsilon 0. That's the simplest solution of Laplace's equation. If there is a line charge, I know potential is log r. That is the simplest solution of the Laplace's equation. So these are the simple cases. Okay, Cosmos says not audible. So I don't know why I'm not audible. I'll repeat. Simple cases are where the symmetry dictates the answer and you can get the answer without actually solving the equation. So for example, if I have a spherical system, a spherical charge distribution, then the solution of Laplace's equation is Q over R.
Audio is not coming, sir.
One sec, audio is not coming. So let's see.
Problem we are encountering, sir.
Just one sec. This is also gone.
Yes, sir. Maybe internet disconnect.
Very poor today.
Yes, sir. We are sorry, sir, about the stylus thing, sir.
No, but also where is the stuff?
Yeah,
This is not on. Okay, it has come.
let's confirm, sir.
Okay.
Let's confirm with the students whether you are audible or not, sir.
Okay, am I audible? Please, please let me know. Am I audible? Okay. So Cosmos, I was not audible. Now I am giving the answer again. You said about the simple solutions. Simple situations are those where symmetry gives you the answer. For example, if I have a spherical charge distribution or a cylindrical charge distribution, by symmetry I already know the answer without solving the differential equation. If I have a spherical charge distribution, right, I can apply Gauss's law integral form and then I know potential, outside the charge distribution is 1 over 4 pi epsilon 0 q over r. In a cylindrical situation, outside the charge distribution, the potential is 1 over 2 pi epsilon 0 log r, right? So in those cases, I know the solution of the Laplace's equation without solving the differential equation, right? So symmetry cases are the simple cases. Okay, now a lot of questions have come. How do I go up?
Just use the mouse.
Okay, so Cosmos, I hope I have answered your question. Now Manish says, we derive the expression for E field and B field energy taking charge and current distribution. But when we come to radiation, we take same equation, there is no current. Okay, very good question, Manish. We derive the expression for the energy, and if you go back to the lecture, I very clearly say we are deriving it from charge, but finally I want to think of it as contained in the electric or magnetic field, because electric and magnetic field concepts become very, very useful, not in calculating the forces and the charges, but when we talk about radiation. There it helps to think in terms of the field being, the energy being contained in these fields. And remember, these fields are being generated by some charge distribution somewhere. So it is that charge distribution that is giving rise to this energy. But now I like to think of it as contained in the field. And it does help that way, because finally when I get the energy from the sun, it is coming in the form of electromagnetic wave. That field is bringing it here, but is being produced there by those charge distributions. Meher Pevrekar, is it, or is it so negligible we can ignore it? Meher, in your case, probably the magnet restriction is very, very small, as is electric restriction. So you can ignore it for fatigue and all that. Fatigue by other means, when you are using a ball bearing, would be much larger. Gaurav Vyas, why we say charge is quantized if we have quarks which are not integral multiples of E? Very good question, but quarks are not free. The free charge is minimum IC is electron. Quarks are not free. They have some, they're bound. So you never see a free quark. So in that sense, they are quantized. If we could see free charges, we'll say they are quantized in E by 3. Chandan Jha, sir, aapka आवाज कट कट कर आ रहा है. Chandan, I hope it's okay now. Yeah, video is just loading and loading. No, now I think it's okay. Okay, Chandan says I should make a course for HC Verma course site. If he asks me, I'll make it. I mean, it doesn't really. Okay. More questions? Okay, I'm waiting for questions. See if there are more questions. Okay.
Then we can conclude, sir. Let's wait for 1 minute, and then if they are not posting any questions, we can answer.
See if there are more questions.
Yeah.
Oh, we can go down.
Yes.
Move it. Okay, questions on electromagnetic theory. I mean, we can have other discussion many times. Oh, sir, please explain the continuity of E and D at the interface of two dielectric slabs between parallel plate capacitors. Okay, now this is a very interesting question, and I also answered this in the forum, and I'll answer this again. If you don't understand, ask me in the forum again. You see, D, when we derived it, D was introduced. D is not the field. D is an effect of only free charges. It's a derived quantity, right? Now, if there are no free charges, then del dot D is 0. And by Gauss's law, perpendicular component of D would be continuous, because Gauss's law is related to perpendicular component on the box across the surface. As far as E is concerned, E is given by both the charges external and the bound charges which are generated. Right? So, in a dielectric, there are always bound charges. So, we say that E parallel is continuous, and that is because E parallel across a surface, suppose there is a surface and E parallel here, E parallel here, the potential difference between 2 points should remain the same, no matter what, whether I do it from this side or this side. The potential difference is the work done. Work done, this distance is the same, so electric field should be the same. So, parallel component of electric field remains the same. That is the boundary condition of electric field. Mathematically, it can be derived by curl of E being 0 in charge-free region or anywhere. Curl of E being 0 means that by Stokes' law, integral across this L, across this closed loop, I'm showing this surface by hand, is going to be 0. And this is contributes nothing, so across this, the integral of E dot dl is the same. That's so that's equivalent to saying that potential difference is the same. For D, there are no free charges and D perpendicular has to be 0, because if I take a box here, right, small box, the perpendicular component on two sides should be the same. Okay, Manish, visit EDX and Corsa, they are far better than Mookit. Manish is very good. Okay. All right, more questions on electromagnetic theory? Okay, if not, then I'll stop. But I'll again urge you, whenever you are studying physics, please make a picture, create an image in your mind, and then you can start seeing things. Physics is slightly more difficult than mathematics because you have to start seeing things and physically see what's happening, and then you formulate it mathematically. Okay, thank you very much. It was fun to interact with all of you through the forum, and maybe we can do it once more.
Yes, sir.
If you require, we can do it after a week or 2 weeks again before the exam, if you want. All right. And then I'll see you on the forum. We'll discuss there. Thank you very much.